Good morning, everyone. My name is Wan Yi, and I come from the College of Intelligence and Computing of Tianjin University. I will present humanCoser, a novel framework to generate physically layered 3D humans from text prompts. In gaming and AR or VR applications, it is important for users to change and transfer their digital humans' clothing and wearable gear in arbitrary and diverse ways. Our goal is to generate high-fidelity layered 3D humans with the ability to change clothes. First, most of the approaches for 3D human only produce a unified surface encompassing both the body and clothing, which lead to a body-clothing coupled, and limit the ability to edit clothing and body separately. In addition, some of the soda-layered human generation approach fails to realize the free transfer and the physical decoupling for clothing. The work in the previous row are coupled generation methods. The work in the latter row are later generation methods. Our motivation is the high-fidelity 3D layered human generation and editing can be performed intuitively and easily by using text prompts. So, we are faced with the following two issues. First, how to generate representation decoupling and animatable 3D dressed humans with consistent body structure in a layer-wise manner. So, we propose a dual representation decoupling strategy to improve the semantic consistency of generated clothing, combined with an innovative multi-layer fusion volumetric rendering approach. Second, how to achieve the geometric matching of human bodies and clothing in an implicit manner. Our solution is to present a 3D implicit deformation field, leveraging SNPL as a clothing proxy for matching clothing with the body. The clothing can be exchanged between arbitrary bodies through this method. Our approach contains two stages: 1, the stage of canonical body generation, and 2, the stage of decoupled generation and matching. Firstly, the sampling points of the observation space are transformed into the canonical space to generate the body geometry. In volume rendering, we introduce an optimizable spherical harmonic lighting to eliminate the oversaturation issue of SDS loss. Finally, SDS loss is updated and optimized for the forward nerf network to complete the generation of a minimized body in canonical space. In order to generate layered clothing that is semantically consistent with the prompt, we propose a dual representation decoupling framework. We add an additional combination of body and clothing representations on top of the single SDS loss supervision of clothing and use another diffusion model to supervise them. Meanwhile, we propose SMPL-driven implicit deformation networks, which can ensure that the body can be matched with arbitrary shapes of clothing so as to realize the exchange and reuse of clothing. Next, I will describe the main modules of our method. First, I'll describe the multi-layer fusion rendering of our method. In order to fuse the layered human body and clothing for rendering, we proposed a multi-layer composite rendering method based on the density and weight of each sampling point. We extend the rendering of the nerf as shown in equation 2, where C'R is the color of each ray, Wij is the weight with the highest density in the n-layer component, and Cij is the corresponding color. By ordering the semantic weights of the n-layer components, the multi-layer humans are finally rendered combinatorially. Secondly, I'll explain the dual representation decoupling framework (DRD) of our method. In order to accurately obtain the shape of clothing, we introduce a dual representation decoupling framework (DRD) to eliminate the parts that are inconsistent with the semantics of clothing. Its advantages: excessive denoising results due to SDS loss can be eliminated, which will keep the generated clothing results consistent with the text prompts. It is possible to physically decouple and reuse clothing and the human body. The DRD model consists of a multi-layer component composition network and a clothing generation network. As shown in the red box of the figure 3, we decouple the representation of clothing and human body by using N-nerf instances. During the training of the clothing component at the NTH layer, we take the density of the sampling point with the largest weight in the first N1 layers as the combination density of the first N1 layers. This combined density is defined equation 3. Finally, as shown in equation 4, we perform a composite rendering of the NTH clothing component and the first N1 components based on the equation 2 of multi-layer fusion rendering. Apart from utilizing SDS loss to supervise the composite rendering results, we also employ a single volume rendering combined with diffusion model solely to supervise the clothing, as shown in the red box of the figure 4. After using the above decoupling strategy, we thus get clothing that is disentangled with the body. Figure 5 shows the effectiveness of the dual representation decoupling framework. Our findings indicate only utilizing a single SDS loss alongside a single volumetric rendering fails to accurately decouple the clothing from the human body and may result in incorrect clothing shapes as shown in the red box above. In order to perform fine deformation of the clothing shape to fit the body, we introduce the SMPL-driven implicit deformation network SIDNet. Given the body SMPL parameters beta, theta, we render a mesh proxy of the body as a binary mask. At the same time, we render a mesh's proxy of the clothing as binary mask images where we use the SMPL model, excluding vertices of the head, hands, and feet. Then, since the body masks should be within the region where the proxy of clothing and the clothing rendered by NERF are merged, we perform the optimization using the loss function 9. Finally, our method calculate the geometric deviation between the clothing and the human body and use the Pound's linear blend skinning to drive the implicit field of the clothing to match the human body. Equations 10, 11 are the corresponding the Pound's equations. This is the effectiveness of implicitly deformed modules. As shown above, the clothing can adaptively match different shapes of body by our method, including even extreme body shapes, for example, the super fat woman. In the following, I will show the quantitative and qualitative results of our work. This figure 9 shows the decoupled generation result of human body and clothing by our method. Here, we provide a comparison between our method and the humanLIF for layered 3D human generation. Our approach can generate bodies and clothing in a layered manner, and the generated clothing can be matched to different shapes of the human body by fine-tuning the deformation module. In addition, comparing to humanLIF, our approach also exchanges clothing between human bodies with different people without retraining the network. Figure 11 shows that our method has better generation quality, even in coupled generation mode. Table 1 shows the quantitative comparisons with non-layered and layered methods by FID and clip score metrics. And Figure 12 shows the quantitative comparisons with non-layered and layered methods user preferences metrics. From Table 1 and Figure 12, we can see that our method has better generation quality and text alignment than the comparison methods. Table 2 quantitatively compares our approach with the non-layered and layered methods through user study. Our method achieves optimal scores across all three metrics, indicating superior generative quality for geometry and texture based on text inputs. As shown in Fig 13. By incorporating additional SDS to supervise the combined results of the human body and the clothing, which enables the elimination of redundant non-clothing parts and maintains semantic consistency with the clothing. And, as shown above, Our SIDNet can optimize the SMPL proxy model of the clothing to deform the implicit field of the clothing to match the body by calculating the shape deviation loss between the clothing and the body. Figure 15 illustrates that integrating spherical harmonic lighting enables the human model to achieve the correct coloration and a smoother visual effect. Finally, I present the related applications of our method. Since our method allows clothing to adaptively match different shapes of the human body, it can be easily applied to virtual try-ons in game dressing and so on. In addition, ours method learns a generalizable density-weighted network, which refines the SMPL-based pose deformations and supports SMPL-driven animations in complex poses without additional training. Finally, I will summarize our work. We propose a layered 3D human generation framework with a multi-layer representation decoupling method. We propose a dual representation decoupling strategy to improve the semantic consistency of generated clothing, combined with an innovative multi-layer fusion volumetric rendering approach. We propose a 3D implicit deformation method based on SMPL vertex prediction to achieve the geometric matching of human bodies and clothing in an implicit manner. Thanks for your attention.